Hey everybody, video number 5, measuring heat in calorimetry. You'll be able to track the changes in phase for water using physical constants. We're going to use 2 different reference tables, and this is going to be a long video, so brace yourself. There's a lot of examples I got to get through to make sure you can use all 3 equations. And I put a generic 4th in to set you up. So first, this is a PBoM calorimeter. This is what we use to measure that heat. And you notice there's a thermometer in the water, and that little cup that's capped in the bottom is what's called the bomb. And I put oxygen in there. It's a sealed bomb, and I can ignite it, and I can burn whatever's in there. And the heat is going to leave that and go into the water, and the change in the temperature is going to help me figure out the heat, especially if I know the mass of what I put in. Okay, so that's how that thing works. Calorimetry is simply the measure of heat, and the calorimeter is what I use to measure it. And that was a picture there of it. Okay. There are equations for heat, and there's 3 of them. They are all on table T, and table T looks like this. At least this piece of table T. I cut it out. It's like kind of towards the bottom of the page. Notice there's 3 heat equations, all in terms of Q, where Q is heat, M is mass, and then I have these other variables. We're going to learn all about those variables, how to find them, and how to plug them in today. Ready? Let's do it. This is what I call MCAT, because that MC delta T. Delta means change in temperature. And I'm going to use this whenever in the problem there is a temperature change. So there'll be like 2 different numbers for temperature in this. And the nice piece, though, is I don't have to convert Celsius to Kelvin or Kelvin to Celsius, because a change in temperature in either is the same number. So we're good there. Okay. H sub F is the heat of fusion. So I use this for fusion or melting or freezing. And the nice piece there is fusion and freezing both start with F, which I believe is that, so that you can pick that one out pretty easy. Okay. Basically, if I'm at 0 degrees Celsius. H sub V equation is used for vaporization or boiling or condensation. And vaporization at least has the V, but here's where I'm going to use it for water at 100 degrees Celsius. If I'm just at 100 degrees Celsius, 1 temperature, H sub V. 0 degrees Celsius, 1 temperature, H sub F. 2 different temperatures because I'm changing temperature, delta T. That's the game. We're going to get some practice. You'll feel more confident once you do a few of these. So some of those variables that are hidden in there, this is on the front page of your periodic table on table B. Looks like this. And unfortunately, it gives you the full out words. So it says heat of fusion, doesn't say H sub F. It says specific heat capacity of water, doesn't say capital C. Okay. And that's one of the problems I find with this particular reference table, that it's on the front page and on the back page, which is a pain in the butt. And then they don't give you the straight up variable there. Like it should say heat of fusion H sub F is, right? And that would make it easier if H sub F was at following that bolded, but you're going to figure it out. So by definition, specific heat capacity of water is the heat needed to raise the temperature of 1 gram of water. 1 gram of water is 1 milliliter of water, 1 degree Celsius. How much heat do I need to change 1 gram, 1 degree Celsius? That is what we call the specific heat capacity. It's a constant. The constant is this: C equals 4.1 joules over grams times Kelvin. Okay. Heat of fusion is the amount of heat needed to fuse or melt 1 gram of water. So this is 334 joules per gram. Kelvin's not in there. Okay. And H sub V is the amount of heat needed to vaporize or boil 1 gram of water, and that is 22.60 joules per gram. And these constants you do not need to memorize because they were in that reference table. You just need to use the right equation with the right constant and the right time. That's all you got to do. So first I have this heating curve that we did last video. And of course, temperature is on the y-axis. And I just draw, remember, 3 slants with 2 flats. And remember, it was solid, liquid, gas, and with the phase changes in between. Well, I can apply the Q to these. So H sub V, heat of vaporization, is at boiling. And where's the boiling point? The top line. So if I'm there, I use H sub V. And H sub F, heat of fusion, is at melting, which the fancy science word for that is fusion, which is there, or condensation if I'm going the other way. Remember, it's the same point. So if I'm going down, it's just called condensation, but I still am at 0 degrees Celsius for water. Okay. And then everybody else, the temperature is changing because I'm on a slant. So I'm going to use MCAT here, here, and here. Okay. Good. Deep breath. Let's learn how to use these things. Oh, we're going to do it again for cooling curve first. Okay. So same thing, guys. Same game. Again, I'm going to go through this one a lot faster, save some time because it's a long video. H sub V is at the condensation point. H sub F is at the freezing point. Freezing F, that helps. And then MCAT's going to be at all of the slants. So it doesn't matter if I'm heating or cooling, these things stay in the same spot, which is hopefully comforting. That it's not all just messed up because I changed it from heating to cooling. Okay, so hopefully that's comforting and makes sense. Delta T. This is, I'm going to start with this because sometimes there is two-step problems where you actually have to solve this piece last because it gives you the final temperature but doesn't tell you the initial temperature, or doesn't tell you the initial temperature but tells you the final temperature, and you just end up solving for delta T, and then you have to plug back into this equation because you had the initial or final, and you solve for the delta T, and then this is the second step. I'm going to just start with this so you get some idea of what delta T is, and then we'll get into the three main equations. So there is my equation. Delta T is always final minus initial. And it says a sample of water is heated from 70 to 90. So my equation, delta T, copy it down, please, and then plug it in. I go final is 90, initial is 70, 90 minus 70 is 20 degrees Celsius. Okay. When I go from cooled from 40 to 20. Now cooled, I don't just do 40 minus 20. Final minus initial. Cooled from 40 to 20. So 20 is now the final, 40 is the initial, and now I have a change in negative 20 degrees Celsius. See why order is specific, because I need to know, am I heating or am I cooling? Positive or negative? Heating, endothermic, positive. Cooling, exothermic. Did I get that right? Cooling, heat is exiting the system. Yeah, got it right. Okay, so here we go. First equation, MCAT. I'm just going to call this MCAT for short because that's what it looks like. Notice in the problem, the water is changing temperature from 50 to 60 degrees Celsius. That's my change in temperature. So there's my cue to use this particular equation. I'm not going to tell you which equation to use when you see this. When you finally have experience with these and you feel uncomfortable, you're going to have to figure out on your own which one to use. Here's your key. Change in temperature, delta T. Boom. So I'm going to use the delta T equation. Now I'm just going to plug and chug. From the equation, I see that there's 100 grams. So that's your mass. C, I pull that off the front page of the reference table, 4.18. Change in temperature, 10 degrees from 50 to 60. Multiply those together. That's why I just put the dots in there for multiplication instead of X's. And I get 4,180 joules. Doing good, milks. Let's keep it up. Next one. I'm going to change now from 90 to 50. Okay. So that right away tells me delta T. There's my equation. I'm going to use MCAT. I'm going to plug in, but this time I have 100 grams. Okay, good. C is the same, 4.18. But this time my change is negative 40. I went from 90 to 50. So I went down 40 degrees Celsius. So I'm going to plug those all in, multiply those all together, and I get negative 16,720 joules. Good. All right, we have two more equations to get to, and then we should be, I think, done with this video. I know it's been a minute, but there's a lot to cover, so we got to make sure we do it. All right, so now I got to decide between H sub F or H sub V. So how much heat is absorbed to melt? 100 grams. So that piece kind of didn't make it into your packet, so you need to write that 100 grams in because we, of course, need the mass to be able to do these. And then the key word here is melt, and the scientific word for melt is fusion. So I'm going to need to use the H sub F equation. I'm going to put Q equals mH sub F as my equation. Now I'm going to plug and chug. Take the 100 from the problem, 334 from my constant, multiply them together, What's nice there is it's just 334 with two zeros. 334 with two zeros. 33,400 joules. Now, same amount of water. I'm sorry, different amount of water. We'll go to H sub V in a second. I was hoping to do the same amount right next to it and see the difference. But H sub V to vaporize is just a lot more energy is the point. So mass of 50 grams for this problem, same problem otherwise. Freeze is H sub F, right? Freezing point. So I'm going to use the H sub F equation, plug it in 50 grams times the constant H sub F, which is 334, and I get 1,600 or 16,700. Hope that's right. I had before. Half of it. So perfect. Just double check. All right. So on to H sub V. These problems. First off, mass of 100. So this will compare directly to the first one we just did now, and you'll be able to see the difference because it's the same mass of water. But it says vaporize. Ooh, that was supposed to say vaporize right there first. Sorry. We switched. But vaporize tells me H sub V. Okay? So I plug H sub V into my equation. Now it's just plug and chug. 100 comes down into my mass. Look up H sub V, 2,260. That is that number with two more zeros on it. Do math quick. Bam, there we go. All right, how much released? How much heat is released when we condense a sample of 30 grams? Well, condense is H sub V. That is going from gas to liquid, which is the boiling point. Okay, you'll see a lot of these in the Regents questions. They'll say at 100 degrees. That's another key. Okay, for vaporizing. For heat of fusion, it'll say 0 degrees. So I'm going to plug into my H sub V equation, my 30 grams times my 2,260, and I have 6,000 or 67,800 joules. It's a lot of joules. You can convert these to kilojoules, which is divide by 1,000, which would be what, 67.8 kilojoules. If you want to write smaller numbers, you got to write bigger units. Those are equivalent statements, so you could do that. And I'm guessing that we are, yes, done. Finished. So there's a lot of practice problems with this particular assignment. I need you to do them earnestly so that you can differentiate between when do I use which equation. That might be one of the single biggest hangups for the entire unit. So practice, practice, practice.